Hello, I am BhaumiK Muliya, currently pursuing first year B.Tech ICT at Marwadi University. So, today's task is design and simulate JFET amplifier using voltage divider bias circuit. This was guided by Mr. Chandrasingh Parmar, who is Head of Department of ICT, Information and Communication Technology at Marwadi University. So, let's simulate on multisim. So, this is the multisim and this is the circuit. So in the circuit, this is the oscilloscope, this is the function generator, this all are capacitors, this all are resistors, and this all are multimeters. Here is one battery also, and ground. And this is the N channel JFET. So now, I have given as an input 1 kHz signal and amplitude was 5 milliwatt peak. So the green one was my input signal. Here you can see this is the input signal, and the red one is my output signal. So this is the output signal. So in a T1, this is the T1 and this is the T2. Here is the value T1 and T2. So input signal is given to the channel B and the output was given to the channel A. So here the input was -4 milliwatt and the output was 20 milliwatt. So this is the voltage. My input signal was 4 watt peak and my output signal is 20 milliwatt peak. So from -4 milliwatt to 20 milliwatt it has amplified. So now we need to measure the gain of the circuit. So for measuring gain we need to get a ratio of output voltage upon input voltage. So let's calculate the gain. Here my output voltage is 20 milli. So 20.7 milliwatt divided by the input which was 4.9 milliwatt, around 5. So in multisim mine gain was 4.22. This is the gain of my circuit. So now let's learn more about JFET voltage divider biasing.
In this video, we will understand voltage divider biasing of JFET. The basic configuration, as you can see, is already drawn and it will be same as BJT. The only difference is that in the place of common emitter BJT, we have N channel JFET. This is the N channel JFET. You can identify the N channel by this arrow. The DC analysis will be different. So now let's perform the DC analysis for this circuit. Now we need to make some changes in the circuit. As you can see, 3 capacitors C1, C2 and C3. Here C1 and C2 are coupling capacitor and C3 is the bypass capacitor. As you know, in the case of DC signal, the capacitors behaves as an open circuit. So let's remove the capacitors and make it open circuit. So this is the open circuit. We don't need to show these terminals. We can remove it. Now the circuit looks like this. Here you can see this is the VDD which was given to both of these terminals. So we can separate this and make a two batteries value VDD at this terminal and at this terminal. So now I am removing this. So this is the VDD, same VDD, and both are grounded. Very important point regarding JFET is that the gate current is IG is nearly equal to 0. So this is the property of JFET, and because of this the resistor R1 and R2 are in series. So the current through R1 and current through R2, current through R1 is I1 and current through R2 is I2. So I am making both of the currents. This is the I1, this is the I2. So these both are in series, so we can write that I1 is equal to I2. So now applying KCL at this node, sum of incoming current is equal to sum of outgoing current. So in our case we have three currents, I1, IG and I2. So I1 is incoming current and it is only incoming current, and IG and I2 both are outgoing currents. So we can write that I1 is equal to I2 plus IG. As you can see, IG nearly equals to 0. So we can write that I1 is equals to I2 because this is 0. Now we can easily find the voltage drop across R2. So potential here is Vg because of this was gate, and the voltage here is VDD, and the voltage here because of grounded 0 volt. Find out the voltage across R2. We will find the equivalent resistance. The equivalent resistance will be R1 plus R2 because both are in series. So equivalent resistor. So the total current will be equal to I. So I1 is equal to I2, and we can write that both are similar with I. So I is the same current flowing from R1 and R2. Find out the I, we will use Ohm's law. Ohm's law is current is equal to voltage upon resistance. So by this we can write that I is equals to VDD upon R1 plus R2. This is the total voltage drop between the ground and this VDD battery, and this is the equivalent resistors we have find it here. So now we need to find out the voltage across R2. So the voltage drop across R2 is I into R2. Here I is VDD upon R1 plus R2. Now we will put it here, VDD upon R1 plus R2. And this is R2. This is the voltage across R2. So now here is the Vg and this is the ground. So the voltage drop on this branch is Vg. So it's similar to this voltage drop across R2. So we can write that this is equal to G. So now we will find out the input voltage VGS. VGS. And for this I will apply KVL in the input loop. So now we will find out the voltage across G and S, gate and source. This is the input voltage drop for JFET. So voltage across this is VGS. And I will apply to find out VGS KVL on this loop. So here I will apply KVL. So now I am applying KVL at this loop. So by KVL I can write that the voltage drop across this was VG and the polarity of VG was plus here and minus here because this was ground and this is the plus volt VG. And the polarity across here is this, and the current across RS is IS. So now the current across RS is the source current, so I can write here IS. Here is the drain current, so I can write here ID. But here you can see that this was 0, here is it, no current. So the current fully ID was here, so I can write that ID is equal to IS. So now here for KVL I can write that plus VG minus VGS, and the current here is ID, so minus ID RS is equal to 0. So from this equation we can find out the input voltage drop VGS. So I am making the subject VGS, so I can write that VGS equals to VG minus ID RS. This is the input voltage drop for JFET. Let's find out the gain for this JFET configuration. Gain is the ratio of the output current to the input current. So by taking AC equivalent circuit, we get that VGS is equals to V input. Also, as the output impedance in equal to RD parallel with RD, small rd parallel with capital RD. Here you can see small rd is parallel with capital RD. That was the output impedance. So VO, V output is equal to minus GM into VGS parallel with RD parallel with capital RD. This is the output voltage. So here the voltage gain AV is equal to output voltage upon input voltage. So we can write that minus GM into VGS into RD parallel with capital RD upon input voltage VGS. Here VGS, VGS cancel. So finally, gain is equal to minus Gm small rd parallel with capital RD. This is the gain. So now I will take the conditions. So the first condition is if the RD is greater or equal to 10 times of RD. So by this equation we can write that gain is similarly equal to minus Gm capital RD because of parallel resistance, as Gm is equals to dID upon dVGS to Q point. We can write that Gm is equal to d upon dVGS. ID's value is IDSS into 1 minus VGS upon VP whole square. So, solving the gain, we can get that Gm is equal to 2IDSS upon mod of Vp in the bracket 1 minus VGS upon Vp. Here the voltage gain AV is equal to voltage of output and voltage input is equals to minus Gm into RD. Here the RD used this and Gm's value here. So now putting this value into this, we can get that gain is equal to minus 2 IDSS upon mod of Vp multiplied 1 minus VGS upon Vp. This is the gain.
So now I hope you understand all the concept of voltage divider biasing of JFET. So thank you for watching this video.